Here's a problem with a more complex geometry to it. What we have is a trough. It has a triangular cross-section. As a matter of fact, those triangles are isosceles triangles. The trough has a length of 12 feet. The cross-sections don't change as we move down those 12 feet. The cross-section, or the ends themselves, have a width of 3 feet and a height of 3 feet. Again, these are isosceles triangles. And water is being pumped into this trough at a rate of 2 cubic feet per minute. Our question is, how fast is the water level rising when the height is exactly 1 foot? So the h in our drawing is 1 foot high. How fast is h changing as we pump this water in? Well, the first thing we need to do is come up with an expression for the volume of this tank. So we know that the volume is going to be its length, which is 12, times the area of the triangle that we see at the end, which is going to be some kind of base times some kind of height. So the volume in general is going to be 6 times base times height. But that gives us a volume function that is a function of 2 different independent variables. We don't know how to do anything with that. We need to try to figure out how to deal with this in terms of a single variable. So we need to find a way to equate, or relate is a better term, the base and the height. Now if we take the base as being the top, we can see that the base is 3 feet. And we can see that the height is 3 feet. But what if we want to find out what the base and the height are for just the water in the trough right here? We're not necessarily interested in the entire trough. We're interested in the part that's filled with the water. So how can we come up with a relationship between the two? Well, if we look at what we have here on the end, we have a pair of similar triangles because we have kind of the smaller triangle with the water embedded in the larger triangle, which is the trough. So since we have a 3-to-3 relationship between base and height for the larger triangle, and the smaller triangle is a similar triangle, it's going to have that same 3-to-3, or easier, 1-to-1 relationship. That is, whatever the base is, the height will be the same thing. Now, since we're trying to work with something involving height, we're going to want to replace base with height, and we'll end up with the equation v is equal to 6h squared, since b and h are the same thing. Again, I'm choosing to make this function in terms of h because I want to find out things about h. I know something about the height h. I'm also trying to find out the rate of change of h. So b doesn't help me with any of that. Don't care about the base. I'm interested in the height. So once we have our equation, we can take derivatives on both sides with respect to time, and we'll end up with the change in volume is equal to 12h times the change in the height. We're looking for the change in the height, so I could rewrite this as dh dt is equal to the change in the volume divided by 12h. In this case, the volume is changing at a positive 2 cubic feet per minute. The height is 1, and we're going to end up with 1/6 of a foot per minute, or if you prefer, we could say 2 inches per minute. Always be careful with problems like these and your units. If we'd been told that h was 12 feet, we would have had to be careful with the fact that, or excuse me, not 12 feet, but 12 inches. If we'd been told that h was 12 inches, and we knew that the change in the volume was 2 cubic feet per minute, we'd have to change that h into feet in order to make the problem work. So be careful and follow your units through here. Most of the problems on related rates that you'll come across, the units should work out pretty well. But it's still an issue that you should keep an eye out for, especially if you apply these ideas in other classes.